1.1 says the impulse delivered by a net force acting on an object is equals to the. So let's talk about impulse. We know fully well that impulse is the change in momentum, right? So the question is saying the impulse delivered by a net force acting on the object will be equals to what? A says the initial momentum of the object, B says the final, C says the change in the momentum of the object. We don't have to go any further. We know that the answer is C, right? Impulse is the change in the momentum of an object. And then D says the rate of change in momentum of the object. That is the net force itself, right? The rate of the change in the momentum. Here we're only interested in the impulse, which is the change in the momentum of an object. And 1.2 says the graph below represents the relationship between the net force exerted on an object and the displacement it undergoes, right? The net force and the displacement are in the same direction. And then we have a graph there. And then which one of the following statements can be deduced from the graph? A says the area between the graph and the displacement axis represents the net work done by the force. Let's look at it and see if it's true, right? We know that work is equals to force multiplied by the displacement and cos of the angle between the direction of the displacement and the force that is acting. We are told here on this question that the force and the direction are the same, right? They're going in the same direction. So the angle will be 0, and cos of 0 we know that it's 1. So the work done will be equal to the force multiplied by the displacement. The area of this graph will clearly be equals to the force, right, on the y-axis. So we have force and then the displacement on the x-axis, right, which is delta x. Is a rectangle, so the area is length times breadth, right? And this is clearly equals to the work done by the force on that object. So we go in with option A. Let's see if option B, C, D makes any sense. Option B says the area between the graph and the displacement axis represents the power. F multiplied by delta x is not the power, so there's no way that can be true. And then C says the gradient of the graph represents the change in kinetic of the object. That is not true. And then they say the gradient of the graph represents the work done by the force. It's also not true. So A is definitely our option here, right? We already know. We just disproving all the other options. And then 1.3 says the diagram below shows all the forces acting on an object being pulled to the right by a force F acting at an angle theta to the horizontal. Which of the following expressions can be used to determine the magnitude of the kinetic frictional force acting on the object? This is one of the equations I really like, right? Because most people get them wrong. So we know fully well that the kinetic frictional force will be equals to the coefficient of the friction multiplied by the normal force. Nothing is said here about the coefficient of the static friction, right? So it will just remain as it is. So what we essentially doing in this question, we finding the normal force. Can you find the normal force when the diagram is like this? So physics 101, free body diagram, right? So let's have a free body diagram of all the forces acting on the vertical axis so that we can determine the normal force. So which forces are acting? We know that the normal force is pointing up, and then we know that the weight is going down, right? But then not only is the normal force acting up, there is a force F that is acting at an angle, right? But then, lucky for us, we can resolve this force F and find the vertical component and the x component. So we're going to have the x component going like that, and then the vertical component going up, right? So now you can see that the normal force plus the vertical component of the applied force is equal to the weight, right? So now the normal force becomes the weight minus the vertical component of the applied force. But then how do we find that vertical component of the applied force? We say the force multiplied by sine of theta, right? And which option is that in our options? So we have the work, so we have the weight minus the force. So that is clearly option B, right? So the answer for 1.3 is definitely B, right? But then what happens if the force is acting down and not acting up? Story for another day. And then 1.4 says the position time graph below represents the motion of a ball from the instant it is released from rest from a certain height above the floor and bounces off the floor a number of times. Ignore the effects of air friction, right? So our ball is released from some height, right? And then we hit the ground. So here we definitely take in down as positive, right? And then it bounces off, reaches maximum height, goes down again, hits the ground, and then goes up, and then it goes down to the ground again. And then the question is saying which point PQRS on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce, right? So here, this is where it's released, and then it hits the ground and bounces off for the first time, right? And then maximum height goes down again, hits the ground and bounces off for the second time, right? So the maximum height reached after the second bounce is at point S, right? And that is option D. So for 1.4, our answer is D, right? If the question was saying after the first bounce, then our answer would be Q, which is option B. But then here we are interested on the second bounce, which is option S, right? And then that is D on our multiple choice. And then 1.5 is saying the kinetic energy of a car moving at velocity V is K, right? The velocity of the car changes to 2V. What is the new kinetic energy of the car? So here I usually advise people to give these variables values, right? Because if you work in variables, most people can't do it, but I can, and I'm gonna show you how. So for the first instance, we have our velocity being equals to V, right? And then if we calculate the kinetic energy there, we're gonna get 1 over 2 the mass V squared, right? But then now the velocity has changed, and then it's now 2V. So what will be the kinetic energy? 1 over 2 m, and in place of V, now we don't have V anymore, but we have 2V, right? So we have 2V squared. So we're gonna get a half the mass. What is 2V squared? 2 squared is 4, right? And then a V squared is V squared. So now we have a half multiplied by 4. So we're going to get 2mv squared, right? So from a half mv squared to 2mv squared, right? How is the kinetic energy of the new car different from the first car, right? It's 4 times greater, because you can easily say 2mv squared divided by a half mv squared. This should be equals to 4. mv squared and mv squared cancel out. We have 2 divided by half, which is equals to 4. So the kinetic energy is 4 times greater, right? And that is option D. And then now let's do 1.6. 1.6 says that a sound source approaches a stationary observer at constant velocity. Which one of the following describes how the observed frequency and the wavelength differ from that of the source? Before we even look at the options, let's look at the concepts first. We know fully well that if a sound source is moving, it's approaching a stationary listener, right? Then the listener will experience a higher frequency, right? And then what is the consequence of a higher frequency? The consequence of a higher frequency is less wavelength, because they are inversely proportional to each other. So we're looking for an option that says higher frequency and less wavelength, right? Option A says the observed wavelength will be greater than. So that cannot be true. We know that it's supposed to be less than, right? And then B says the observed frequency is less than, so that is true. And then it also says the frequency is less than. That is wrong, right? C says the observed wavelength is less than, and the observed frequency is greater than. And that's exactly what we're saying, right? So for 1.6 we can go with C. And then 1.7 says the electric field pattern between two charged spheres A and B is shown below, right? We have the electric field pointing towards A and moving out of B, right? So before we go any further, if the electric field lines are pointing towards, then that sphere is negatively charged. And then if the electric field lines are pointing outwards, then that sphere is positively charged, right? Which one of the following statements regarding the charge of spheres A and B is correct? Sphere A is negatively charged, right? We know fully well that that is true. And then sphere B is positively charged. Yeah, that is true because the electric field lines are radiating outwards, right? So before we go any further here, our answer for 1.7 is A. And then 1.8 says the SI unit of the rate of flow of charge in a conductor is. So yeah, back to the concepts. The rate of flow of charge. What is the rate of flow of charge? We know that I is equals to Q divided by delta T, right? So current is the rate of flow of charge. And what is the SI unit of current? Ampere, right? And then which option is that? It's clearly option C, right? So 1.8, our answer is C. Yeah, it's pretty much easy, not so complicated. And then 1.9 is saying which one of the following changes to the design of an AC generator will increase its maximum EMF output. This is actually a grade 11 work, right? When you're talking about electromagnetism, you know that if you want to increase the maximum EMF, then you have to increase the number of turns on the coil, right? And then for 1.9, that is clearly option D. Another way you can do, you can increase the strength of the magnets, right? Not change the polarity, but increase the strength of the magnets. There's other ways too, but stories. 1.10 says a line emission spectrum is formed when, okay, back to the basics again. So emission spectrum, right? So an emission spectrum is formed when we go from higher energy levels to lower energy levels, right? And then an absorption spectrum is formed when we go from lower energy levels to higher, right? Here we're talking about a line emission spectrum, right? So we're looking for higher to lower. Option A says electrons in the ground state moves to a higher energy state. No, that's absorption, right? Lower to higher. Now we want higher to lower. And then B says electrons in the higher energy state move to a lower state. We don't have to go any further. That's what we're looking for.